Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing about an interesting area of organometallic compounds, an interesting type. These are called transition metal perfluoroalkyl complexes. And these are often designated as RF transition metal type compounds, where RF represents the perfluoroalkyl moiety. Now, these compounds bears analogy to the simple transition metal alkyl complexes, which are also given by R T M, where R is an alkyl group, or one may also represent the same as R H T M, where all the alkyls have hydrogen substituents on it, to be more precise. So, transition metal alkyl complexes are represented as such. Both of these compounds may be related in the sense that they are all sigma type bonds with the transition metal, they all make sigma type bonds. However, when one looks at these two compounds, one is the transition metal perfluoroalkene or transition metal alkyl complexes. So, one sees that they differ in their reactivity as well as in property, and that is something which is of interest and needs further discussion. One also finds that these transition metal perfluoroalkyl complexes are more stable than the corresponding transition metal alkyl complexes. And in today's lecture, we will be focusing more on this reason for extra stability of these transition metal alkyl complexes. Now, there is an counter argument which suggests that transition metal perfluoroalkyl complexes may not be very stable, the argument being that the decomposed product of these complexes should be metal fluorides. Are metal fluorides which has high lattice energy and hence this compound should be less stable, because they would want to dissociate or decompose to metal fluorides having high lattice energy. But what it turns out is that these transition metal perfluoro bonds are very strong, leading to their extra stability. And in this discussion, what we are going to focus on is the reason for this extra bond strength of perfluoro transition metal alkyl complexes. So, in order to understand this, let us take a look at this transition metal perfluoroalkyl bond. Now, perfluoroalkyl has all of the carbon substituted with fluorine instead of hydrogen in a normal alkyl analog, and as fluorine being very electronegative, the polarity of this alkyl group thus becomes del minus and the metal becomes del plus, and this is a kind of sigma interaction occurring between this perfluoroalkyl group and the transition metal. Now, as this difference in polarity, or as this bond becomes more polar owing to the presence of the fluorine, then the metal becomes partially more positively charged, which results in contraction of metal orbital, thereby increasing the overlap between this metal C bond. So, high partial charge of metal del plus results in contracted metal orbital, leading to an increased MC overlap, and which gives greater stability. Similarly, for the back donation, for example, from the metal to the ligand, pi type back donation, because of the presence of these perfluorofluorine atoms on each carbon ring, the pi star of the RF fragment become low lying, which also increases the metal carbon back bonding and resulting in a better overlap. So, highly electronegative fluoride atoms on RF moiety makes pi star MO of RF low lying, thereby facilitating metal to RF back donation. And increasing M RF bond dissociation energy. So, what comes to the fore is that the greater stability of the RF transition metal arises because of the greater polarity of the bond, and that affects both the sigma bond as well as the pi bond in the same direction, that is, this enhanced polarity due to presence of electronegative fluoride affects both the sigma and pi bonds towards increasing the corresponding RF transition metal bond energy, and this does so by contraction of the metal orbital as the metal become more partially charged, leading to an increased metal MC overlap for the forward ligand to metal forward sigma donation, and the presence of so many fluoride atoms on the perfluoroalkyl group makes the corresponding pi star mercury orbital low lying, and that also in turn facilitates the metal to ligand pi back donation, and both of these factor working together increases the metal to perfluoroalkyl bond dissociation energy, thereby imparting stability to these perfluoroalkyl transition metal complexes. Now, there are many reactions which are common for simple alkyl transition metal complexes which does not occur in their perfluoroalkyl counterparts, and that can be ascribed due to the increased polarity or the presence of fluoride atom in the perfluoroalkyl moiety, resulting in difference in reactivity. For example, CO insertion in RF metal bond is unfavorable. I will illustrate that with an example. For example, if in a metal alkyl complex of the type M RH M CON, where RH is a simple alkyl group containing carbon and hydrogen atoms, when heated readily undergoes CO insertion into metal RH bond, giving RCO M CO N minus 1, and this reaction happens readily upon heating and is observed in many transition metal complexes, whereas the same reaction in its perfluoroalkyl analog as given by RF M CON is very rare. So, here too such insertion is observed rarely, and seen only at elevated temperatures. So, the reaction which is common for alkyl carbonyl complexes, this reaction of CO insertion into a metal carbon bond is absolutely rare for perfluoro metal carbonyl complexes and proceed at a very high temperature. So, this sort of highlights the difference in reactivity between these two classes of compound, even though structurally they may be very similar in resemblance. Now, I would come to the various preparative methods available for synthesizing these perfluoroalkyl transition metal complexes, and to begin with, the most common method for synthesizing these perfluoroalkyl transition metal complexes is the reaction of perfluoroacyl halide with carbonylate anion. Plus carbonate anion. I will illustrate with this with the following example. Giving rise to this perfluoroacyl MnCO5. Now, here one can see that this acyl group has positive charge at the carbon and the metallate MnCO5 has a negative charge at the manganese. As a result, the formation of manganese pentacarbonyl perfluoroacyl compound is formed, and this when heated eliminates CO, resulting in perfluoroalkyl manganese pentacarbonyl. So, what we saw is that acyl that CO elimination for a acyl bond from a acyl bond occurs upon heating, resulting in the formation of RF MnCO5 along with carbonyl moiety. Another interesting feature about this class of compounds is that reversal of polarity is observed in many of its examples. Let me illustrate this with perfluoroiodides. For example, a perfluoroiodide would have the polarity in the RF bond as iodine having the del positive and the RF minus having the del negative charges. The reason being fluoride being a very strong electronegative element would result in accumulation of electron density on the RF moiety, resulting in del minus on this side and appropriate del plus on the iodide. However, this polarity is completely reversed to that of alkyl iodide. For example, in alkyl iodide, in the corresponding hydrogenated counterpart, here in this case what we see that iodine is del minus and the carbon having all the hydrogen becomes del plus, because iodine is more electronegative. So, these two demonstrate that there is a reversal of polarity if one were to look at this bond or this bond, and no wonder they show very different reactivity, and that is because this RF iodide type of compound favors nucleophilic attack at the carbon, whereas RH type of compound favors electrophilic attack. Let me illustrate this with an example. For example, for the reaction of CF3I plus sodium manganese CO5, here the iodine is in positive charge and the manganese is in the negative charge, and CF3 has a del minus charge and it does not react with the manganese, and the final product one gets is manganese pentacarbonyl iodide plus sodium iodide plus C2F6. This reaction is completely different than what one would have expected with the corresponding hydrogenated counterpart. In that case, the methylated MnCO5 minus would go and attack the methyl cationic fragment of CH3 and not end up on iodine as shown over here. Another interesting example reactivity of these perfluoroalkyl complexes is that the perfluoroalkyl complexes can undergo fluoride substitution with strong nucleophilic methylates. With strong nucleophilic carbonyl methylates. For example, CpFe dicarbonyl anion plus C6F6 gives CpCO2 Fe sigma bonded with C6F5 plus F minus. So, here the methylate anion is substituting a fluoride anion in this C6 F6 moiety. The same can be seen over here, where MnCO5 minus showing similar nucleophilic attack and replacing the fluoride moiety in the cyclobutane compound, resulting in this perfluorocyclobutane fluoride compound and fluoride anion. With this, let me summarize what we have been discussing in today's lecture. We have looked into interesting class of compounds called perfluoroalkyl transition metal complexes. We have looked into their exceptional stability at the for these kind of complexes. We looked for reasons for the source of this exceptional stability, and that arises because of the polarity of the metal carbon bond containing the perfluoroalkyl moiety. We had also seen that this polarity results in more stronger ligand to metal sigma donation and metal to ligand pi back donation, which sort of leads to the stability of these compounds. We have also seen that for case of perfluoroalkyl halide, there is a reversal of polarity leading to different kind of reactions occurring in these perfluoroalkyl transition metal complexes. We have also looked at some of the synthetic procedures available for these perfluoroalkyl transition metal complexes. With this, I conclude today's lecture and look forward to being with you in next lecture, where we are going to take up some more synthetic strategies available for perfluoroalkyl transition metal complexes and look into the reactivity of these complexes. Till then, goodbye and see you in the next lecture. Thank you.